All right, so today we're going to be talking about substitution versus elimination. All right, we've been talking about these reactions of alkyl halides. Okay, and so previously in our previous two lectures, first we talked only about substitution reactions, which take place when you react an alkyl halide with a nucleophile. Then we talked about elimination reactions, which take place when you react alkyl halides with a base. And now we're going to talk about the competition between the two of these reactions, right? So we got these two different paths that our alkyl halides can take, depending on whether we react them with nucleophiles or bases. But there are plenty of reagents that are both nucleophiles and bases, all right? So how do we figure out what's going to happen in the competition between these substitution and elimination reactions? And really our goal here is we're trying to predict products. All right, and what we're going to see is in predicting our products, this is going to depend on both our alkyl halide that we start out with and our nucleophile slash base that we're using. All right, we've talked about our different alkyl halides, methyl versus primary versus secondary versus tertiary. That's going to factor into what reaction occurs, substitution, elimination, or some combination of both. Now let's talk about the other thing, our reagent, our nucleophile slash base here. All right, and really what we're going to be doing is we're going to be talking about different reagents and their nucleophilicity versus their basicity. All right, now strictly speaking, all bases are nucleophiles. All bases work, they accept protons by donating a pair of electrons. That's the definition of what it means to be a nucleophile. Not all nucleophiles are bases, though. Kind of how a square is a rectangle, but a rectangle isn't a square sort of business. All right? However, within this context here, we're specifically going to be referring to our nucleophiles. We're kind of considering its nucleophilicity without the basicity part. So when we talk about our nucleophilicity, really what we're talking about is our tendency towards those substitution reactions. And when we talk about our basicity, we mean our tendency towards those elimination reactions. All right, so when we say that something is a strong nucleophile, that means it's good at substitution reactions. When we say that something is a good base, that means it's good at elimination reactions. All right, and what we're going to do is we're going to take the world of our reagents and we're going to classify them as to whether or not they're strong or weak nucleophiles and strong or weak bases. All right, so we got these four different categories that we're going to be looking at. The first one are going to be our molecules, our reagents that are kind of crappy at both, our weak base, weak nucleophiles. All right, so these are things that, importantly, they can play the role of both a base or a nucleophile. They're just not very good at either of them. Okay. what we're going to see is in order to be a weak base or a weak nucleophile, in order to play that role at all, you must contain a lone pair. All right, if there are no lone pairs, you simply cannot be a base or a nucleophile. However, what is it that's going to make them weak here? Does anybody have an example of a weak base or a weak nucleophile that we could look at the formula for? Water, yeah, that's a great one. Or similarly, we could take that water and replace one of those hydrogens with an alkyl group. All right. And what is it that makes these weak compared to, say, the strong version, like a hydroxide ion? It's neutral. All right, awesome. So our weak base, weak nucleophiles, in order to play the role of either a base or a nucleophile, you got to have a lone pair. But importantly, these are going to have a net neutral charge. All right, now in this example here, what is my nucleophilic / basic site in this water molecule? It's got that oxygen, right? It's got to have that lone pairs. All right, so we can kind of classify these based on that nucleophilic or basic site. Oops. All right, so an atom that we see playing the role of one of these weak base, weak nucleophiles would be a neutral oxygen atom. All right, the cousin of oxygen on our periodic table sharing that same family would be sulfur. Sulfur likes the same bonding pattern, so we could also have a dihydrogen sulfide, or what we call a thiol, where we have an alkyl group on there. All right, or another one would be nitrogen. Nitrogen, we can have ammonia, or we could have one of those amines. All right, importantly, all of these have these hydrogens on there. I got to have at least one hydrogen. Why is that? Thinking of specifically playing the role of a nucleophile. What do we know about these neutral nucleophiles? They could, well, so we're saying they could be proton acceptors because they could be bases. All right, but we talked specifically about our neutral nucleophiles. What happens to our neutral nucleophiles in a substitution reaction? They will necessarily lose a hydrogen. So we got to have a hydrogen that we can lose in order to play the role of a nucleophile here. Cool. All right, so let's just note here, lose hydrogen in our substitution reactions because they're neutral. All right, and now we're dividing the world of these reagents up into these four categories here. Clearly, the world is not quite that like binary or whatever, the analog quaternary, I don't know. Anyways, the world doesn't exactly fit in these nice, neat boxes here. We're calling these all the same box, our weak base, weak nucleophiles. But what do we know about nitrogen in comparison to oxygen? Like water in comparison to ammonia, which one is a better base? Going back to our Fario rules here, oxygen being more electronegative would be more stable, so a weaker base than our nitrogen would be, right? So We know that nitrogen's a little bit better of a base, so we would expect ammonia to favor these elimination reactions a little bit more than water. However, we're going to kind of simplify things by lumping them into these categories here, all of these being lumped into that weak base, weak nucleophile category, all right? So again, we're lying to ourselves a little bit by pretending like the world is this nice and neat and clean cut, but it's going to make our lives a lot easier. So that's what we're working with here. All right, our next category are things that are weak bases, but that are strong nucleophiles. All right, so these weak nucleophiles were easy to spy because of their neutral charge here. So what do we think for our strong nucleophiles we're going to see? A net negative charge. All right, so what is it that makes something a weak base, even if it has that net negative charge? We can think of a lot of negatively charged molecules, but they might also be strong bases. So what's going to be a weak base? There's kind of two features going back to our Fario rules that we would expect to see for these weak bases, meaning that their conjugate acids are nice, strong acids. That means that that conjugate base has to be relatively stable. There are two main factors that we see that stabilize that negative charge, one of which is resonance. So if we have a resonance stabilized negative charge, that would be something that has that negative charge, so it's a nucleophile, but it's resonance stabilized, so it's a weak base. Or the other thing that will stabilize a negative charge is having a really large atom holding that negative charge, right? So an iodide ion is very stable with its negative charge because those electrons are sitting really far away from that nucleus, really spread out. All right. So just to go through some examples here, all right, let's look at a few that are resonance stabilized. All right, again, we need this net negative charge. One good example will be a carboxylate ion, a deprotonated carboxylic acid. Carboxylic acids have relatively low pKa's because their conjugate bases are nice and stabilized through resonance, right? This negative charge can be bounced between those two oxygen atoms, making this a pretty crappy base, but a good nucleophile because of that net negative charge. All right, another example is the cyanide ion. Okay, and then another one that's going to be new to us here, we're going to use this chapter to introduce it, what's called an azide ion, N3. I'm going to draw out this Lewis structure, or rather, I'm going to start it, and y'all are going to finish it here. I will tell you that each of these terminal nitrogens are double bonded to that central nitrogen. I want everybody to take a second and fill in any missing lone pairs or formal charges. right, so these nitrogens on the end here, how many lone pairs am I going to have to give them? 2. They need to complete their octet. If they got 2 bonds and 2 lone pairs, what's their formal charge? Negative onto each side here. But then my nitrogen in the middle has 4 bonds and no lone pairs, so it's got a formal charge of positive 1. So that's how I get this net charge of -1. -1 plus 1 minus 1 leaves me with -1. So these are some examples of some resonance stabilized nucleophiles. They're good nucleophiles because of that net negative charge, but they're not crappy bases because of that resonance stabilizing that negative charge. All right, on the other flip side here are large atoms. So these are atoms holding that negative charge. And what's a quintessential example of something that has a negative charge but sucks at being a base? What up? So one of our larger atoms here, but specifically for those halogens, right? Chloride ions, bromide ions, iodide ions. They're all really big negatively charged ions, but they're terrible bases, right? They're conjugates. Hydrochloric acid, hydrobromic acid, hydroiodic acid are strong acids, meaning that they are weak bases. Remember that inverse relationship between acid strength and base strength. I will say a lot of y'all want to go, everybody wants to go ahead and start reviewing those Fario rules, that acid-base chapter. That plays a little bit of an outsized role on that final exam because it's a very important chapter. You've talked about acids and bases. How many times now over your chemistry career? There's this assumption that you have a good handle on recognizing acids and bases. So if that's not something that you're really good at doing or comfortable with, you want to start reviewing that for our final exam now, all right? Again, it should make perfect sense that this thing right here is a terrible base because its conjugates are strong acids. And again, if you need to review that concept, I would start now. The other atom that we see playing the role of a nucleophile a lot that's not a particularly good base, definitely a better base than these things here, but nonetheless, we're going to throw it into this category, are our sulfide ions. So hydrogen sulfide or a deprotonated thiol. These would be examples of these large sulfur atoms holding that negative charge, making them good nucleophiles but bad bases. All right, and so where are we going with this? If something's a weak base and a strong nucleophile, what type of reaction do we think it's going to prefer? Substitution or elimination? Substitution, right? Weak at elimination, strong at substitution. All right, our next category, are these atoms that are good, are these molecules rather that are good at both? These are our strong bases and strong nucleophiles. Again, they're strong nucleophiles. So what are we going to look for here? That net negative charge. But these molecules can't be nice and stable holding that negative charge, or they would not be bases. So instead of having them be resonance stabilized or large atoms, these are going to be these molecules that aren't resonance stabilized, and they're just these teeny tiny little atoms holding that negative charge. All right, so now we're talking about small atoms holding that net negative charge. All right, and again, we see our common nucleophilic basic sites. All right, our small electronegative atoms playing the role of a good base would be our oxygens. or our nitrogens. Okay, so a quintessential example of a strong base, strong nucleophile is that hydroxide ion. All right, we know hydroxide's a good base. It's also got that net negative charge. It can play the role of a nucleophile very well as well. All right, or we can take an alcohol and remove that proton, so now we have an alkyl group on that molecule. All right, these are what we call alk oxide ions. Not hydroxide with a hydrogen, but alk oxide with an alkyl group. A little bit more rare because it's a way strong base, so kind of dangerous to work with, but nonetheless, are nitrogens with a net negative charge. All right, we're going to name this thing as well. This is what's called an amide ion. We talk about it a lot in organic chemistry. I've only ever seen it on pencil and paper. I've never actually seen it in the wild because it is a very, very strong base and pretty dangerous to work with. Nonetheless, would be thrown into our category here of strong bases, strong nucleophiles, or if instead we replaced those hydrogens with alkyl groups, that would also work. All right, now there's going to be a subtle difference between our strong base, strong nucleophile category, the one that we're talking about here, and our strong base, weak nucleophile category. We're going to see these same basic sites here. The difference is going to be the size of these alkyl groups. Another important feature of these strong base, strong nucleophiles is we have to have small alkyl groups. All right, and that's going to distinguish these between our strong base, weak nucleophiles, all right, because these look pretty similar. In order to be that nice, strong base, we're going to need that net negative charge. And we need that net negative charge to not be very stable, so it's got to be on a small atom. All right, the big difference is these small negatively charged atoms are going to be attached to bulky alkyl groups. All right, so again, we can take an example. We got those same small negatively charged atoms, oxygen and nitrogen. But now we're going to attach this negatively charged oxygen, not to a tiny alkyl group, but to something big and bulky. All right, so there are a few popular ones that we're going to name here. Anything that's really big and bulky will work. All right, but again, there are a few that we see quite often. This molecule right here is called tert butoxide. All right, sometimes potassium tert butoxide or sodium tert butoxide. We have that counter ion there. Importantly, the counter ion isn't actually involved in our reaction, so I don't usually draw it in there because I don't like to confuse. All right, likewise, we could have a nitrogen with a net negative charge, but it's going to be bonded to these big bulky groups. All right, this one they specifically use this lithium counter ion for. I don't know if there's a great reason for that or not, to be honest. But the name of this molecule here is LDA, or lithium diisopropylamide. Okay, but again, what's going to characterize these strong base weak nucleophiles are we have those good basic atoms, those small negatively charged atoms attached to these big bulky alkyl groups. All right, so why is that? Let's compare our small versus bulky bases. All right, and what we're going to do is we're going to take the same alkyl halide here. First, we're going to treat it with sodium hydroxide. All right, then I'm going to take that exact same alkyl halide and instead treat it with the tert butoxide. Okay, sodium hydroxide, of course, being a small base, whereas tert butoxide is one of our bulky bases. All right, and we're sort of working on predicting our products here, but we're trying to right now think about the big differences between these two. All right, what we're going to find is that our primary alkyl halides, even though hydroxide's both a good base and a good nucleophile, these really prefer substitution reactions. And if it's a substitution reaction, specifically which substitution reaction, SN1 or SN2? SN2, because it's a primary. So everybody take a second and give me my SN2 product here. We substitute out that halogen for that hydroxyl group, giving us what functional group in our product? An alcohol. All right, and remember, if this was an SN2, that's because that hydroxide attacks that electrophilic carbonyl carbon, kicking off that leaving group. Right? Okay, so now if we use a bulky base, this does not produce a substitution reaction, but rather an elimination reaction, producing an alkene. All right, but why do bulky bases prefer elimination? All right, well, let's compare these two. Let's say that I was going to do a substitution reaction. Where would my bulky base here have to attack? if I were to do a substitution? That carbon. Okay. Now, importantly, my carbon, as I drew it here, I didn't actually draw all my bonds. What else are located on this carbon? Hydrogens, right? So if I'm being good, I got to show that my bulky base has to make it past these hydrogen atoms in order to even get to that electrophilic carbon. All right? Since it's big and bulky, is it going to have an easy time making it in there? No. Instead, if it were to do an elimination reaction, what would it react with? One of these hydrogens on that neighboring carbon. Well, what's more accessible? That electrophilic carbon buried between those hydrogens and that other carbon bond, or these hydrogen atoms just kind of sticking off on the surface of that molecule? These ones right here, right? So why do bulky bases prefer elimination? All right, because hydrogens are more accessible than our electrophilic carbons. And this was a primary alkyl halide. This is the most accessible of all the electrophilic carbons, right? As soon as I start adding more and more carbon bonds, all of a sudden this becomes even less accessible. All right, so we're just going to make note here. This does not happen. Okay, our bulky base is going to prefer that more accessible hydrogen. I guess I'm going to be good and finish off my E2. That means this pair of electrons comes, and we kick off our leaving group. All right, so we have this very simple accessibility argument here. Small bases / nucleophiles, they have an easy time getting to that electrophilic center, so they can have these substitution reactions. Bulky bases, they do not have an easy time getting to those electrophilic carbons, so they're just going to pluck off one of these hydrogens that are very easy to get to, leading to our elimination product. All right, so now this is going to all sort of culminate here in what's going to be a very important page in our notes here, our substitution versus elimination cheat sheet. All right, so what we're going to do is we're going to make a cheat sheet here where we first look at our different alkyl halides. All right, we have a few different types of alkyl halides. Our primary, secondary, and tertiary. All right, and then we're going to make these 4 categories here for our 4 different categories of our reagents that we've been discussing. All right, we have our strong base, weak nucleophiles. We have our category that is good at both are strong base, strong nucleophiles. We have our weak base, strong nucleophiles. And then lastly, our things that aren't very good at either are weak base, weak nucleophiles. All right, and what we're going to do is we're going to fill this in with whether they prefer substitution or elimination based on which category our reagent is, as well as our alkyl halide. All right, and let me just say that on your exam, one of your very first questions is going to be a blank table just like this, and it's going to be your job to fill in that table. All right, so once we have it all filled in, it's going to be a convenient little cheat sheet to use. However, make sure that you can fill this in from memory here. You're going to have to do that as a question on your exam, and then you can use it on your exam. All right, so first, some of these are a little bit harder than others here. So let's take the no-brainers here. Meaning something that's a weak base, strong nucleophile, we think are going to prefer which reaction, substitution or elimination? For a weak base and a strong nucleophile. Substitution. And so these are all going to be substitution favoring conditions here. All right, we're going to be good and include our exact mechanism. For primary alkyl halides, what is the substitution mechanism that we're going to do? SN1 or SN2? SN2. What about secondary? Also SN2. And what about tertiary? That one will prefer SN1 reactions. All right, so if you suck at being a base, but you're a good nucleophile, you're definitely going to prefer substitution. And based on the identity of our alkyl halide, we know whether it's SN1 or SN2. Let's flip to the other extreme here. All right, our strong base, weak nucleophiles. What are those going to prefer, substitution or elimination? Elimination. So across the board here, we see elimination reactions. All right, now for primary and secondary, it should not be a surprise that these undergo E2 reactions because they don't like to form those carbocation intermediates. Okay, it turns out that for tertiary alkyl halides, although they can undergo E1 reactions, if you have a really strong base present, that deprotonation step is faster than waiting for that leaving group to just fall off, than forming that carbocation. So these will also undergo E2 reactions under those conditions where you have a strong base. All right, so now we have our harder to figure out categories here, our weak, and our strong. Let's look at our weak category first, okay? So these weak nucleophiles here are just weak nucleophiles, weak bases, are just simply not strong enough to react with primary or secondary alkyl halides. They're not good enough at being a base to do an E2 reaction. They're not good enough at being a nucleophile to do an SN2 reaction. All right, so the only thing that they will react with are going to be our tertiary alkyl halides. And that's because these tertiary alkyl halides can form carbocations, which are just really good electrophiles, right? Really good at accepting pairs of electrons. So they can react with these weaks. Okay? Now, it turns out that since they're bad at both being a nucleophile and a base, you get a mixture of your substitution product, your SN1, and your elimination product, your E1. You'll get a mixture of both. And we're going to pretend like it's a pretty even split here. Truthfully, again, devil's in the details. If we had, for example, a water molecule, we would probably expect more substitution product than if we had an ammonia molecule, because ammonia is a little bit better of a base than water. But again, we're kind of breaking the world into these nice, neat 4 categories here. So we're just going to, for the sake of argument and not making ourselves too crazy, say that we get a pretty even split between elimination and substitution. All right, again, devil's in the details of exactly where this dividing line is, but it's pretty much in the middle there. All right, and then the hardest category here are these molecules that are good at both. All right, and so what we're going to see is, since they're good at being bases, we have these elimination reactions that are likely, but they're also good at being nucleophiles, so these substitution reactions are likely. So how are we supposed to figure out what prefers what? All right, the key to understanding this particular category here is going to be steric hindrance of that electrophilic carbon. All right, we scratched on this a little bit in our discussion of these small versus bulky bases. The reason why it's a bad nucleophile, those bulky bases, is because it has trouble accessing that electrophilic carbon. Same thing here. That's going to be our key to understanding this category here. All right? So what we're going to see is that our least sterically hindered alkyl halides, these are going to be the ones that prefer substitution. Whereas our most sterically hindered these are going to prefer elimination. All right, so I'm going to put down an alkyl halide from each category here. And I want you to arrange them from the most sterically hindered electrophilic site to the least sterically hindered electrophilic site, or I guess least to most, as I have them on the page here. All right, and again, I'm talking about that electrophilic carbon, the one that is bonded to that halogen atom. All right, the accessibility of that electrophilic carbon. What's going to be my least sterically hindered? Primary, secondary, tertiary? The primary is going to be my least sterically hindered. And what's my most? Tertiary. And our secondary are kind of sitting in the middle here. All right, so what we're going to find is because of that accessibility of that carbon, our primary alcohols are, not alcohols, primary alkyl halides are going to prefer substitution reactions, whereas our most sterically hindered tertiary alkyl halides are going to prefer elimination reactions. All right? So if we go through here, again, primary prefer our substitution. And so what we're going to see is this split, this uneven split between our elimination and our substitution. All right, to be clear, what I'm kind of showing with these blockings here is that we get a minor elimination product and a major substitution product, right? So most of your molecules react with a substitution mechanism. There are a few that undergo elimination. All right, and this is kind of a big jump here that maybe you wouldn't expect, but it turns out that putting even one additional carbon on the other side here really tips the balance of these substitution and elimination reactions in favor of elimination. All right, so as soon as we get to a secondary carbon, a secondary alkyl halide, now all of a sudden our major product is the elimination product, and we get only a minor amount of that substitution product. All right, so again, with my little dividing lines here, what I'm showing is that now our major product is elimination, and our minor product is substitution. So then based on this trend here, what do we think our tertiary are going to be? More elimination or substitution? Elimination, to the point where now, once you have a tertiary alcohol or tertiary alkyl halide, that electrophilic carbon is just no longer considered accessible at all. It's completely blocked up. Nothing can get to it very easily at all, and so you only have elimination reactions. All right, again, since it's a strong base, our elimination mechanism will be that E2 mechanism. Okay, so this is this little cheat sheet here, where given a reaction, you're going to figure out what category your alkyl halide belongs to and what category your reagent belongs to. And that will tell you what type of reaction or combination of reactions that molecule will, or rather that set of conditions will undergo. All right. Again, this is a really helpful little cheat sheet to use as you're doing your homework. But again, remember that you're going to have to fill in a blank one of these. So make sure that you understand why, for example, we get a mixture of E2 and SN2 for a strong, and a primary. All right. So for right now, let's practice putting this into use here. Everybody's going to take a second and predict the products of these reactions. All right, so let's go through these. Step one, we got to classify our alkyl halide here, primary, secondary, tertiary. What do we got? This is a primary alkyl halide. And our reagent here belongs to which category? Is it a good base? Yeah, it's a strong base. Is it a good nucleophile? No, because it's big and bulky, so it's a weak nucleophile, which means that this is going to prefer those E2 or elimination reactions. All right, now normally with the elimination reactions, we got to worry about all our possible products here. Since we have this primary alkyl halide, our lives are a little bit easier. We just have this one potential product. All right, what about this alkyl halide here? Primary, secondary, or tertiary? Secondary. And our carboxylate ion here corresponds to which category? So it is a weak base, but a strong nucleophile. What is it that makes it a strong nucleophile? That negative charge. And what is it that makes it a weak base? The fact that that negative charge is stabilized across both of those oxygens. So then this is going to undergo what type of reactions here? Substitution, and specifically an SN2. So now we can't throw out everything that we learned previously. Remember, with our SN2 reactions, we specifically have that stereochemical inversion. So my nucleophile is going to be added from the opposite side of where my leaving group was. All right. And what specifically was the nucleophilic site in my carboxylate ion? The oxygen. So that's what needs to be bonded to my carbon here. All right, and then the last one here. This is a tertiary alkyl halide. All right. This has a negative charge here, and it's small, so this would be a strong nucleophile. But is it a good base? No. And what is it that makes it a weak base? Size? Yep. The fact that it's a large atom holding that negative charge. So remember, in our weak base, strong nucleophile categories, what made these strong nucleophiles is those negative charges. What made them weak bases are either resonance stabilization or the large size of the atom holding that negative charge. All right, so these are also going to prefer substitution, but not SN2. These will be SN1. So we have to remember that when we form that carbocation, we're going to lose our stereochemistry about that electrophilic carbon. So we'll get a racemic mixture here that we represent with just our straight line bonds. Cool. All right. So name of the game, figure out the category of alkyl halide, figure out the category of your reagent, and then you're going to that'll then point you to the type of reaction or reactions. For this first set here, I specifically just did reactions with one product. All right. Now let's step it up, do a little bit more complicated. You're going to predict products and label any major versus minor products that we would expect. All right, so let's go through this. First of all, what the hell is this OTS business? A good leaving group. That's the only thing you have to think of when you see this here. Basically, in your mind, you can replace it with an iodide or something like that. It's just going to play the role of a good leaving group. And this is a primary tosyl, whatever. All right. And then this is what? Is it a good base? Holy hell, is this the most amazing base you've ever seen in your entire life, all right? A deprotonated nitrogen is ridiculously, ridiculously strong base, all right? So yes, this is a strong base, but it's also all teeny tiny small, so it's a strong nucleophile, all right? And if we look on our cheat sheet here, that means that we're going to get a combination of both elimination and substitution. So I'm going to put down both. All right, our E2 and our SN2. All right. Do our SN2 product. I'm going to substitute out that tosyl group for that NH2, creating an amine. All right, or I'm going to do my E2 reaction here, where I'm going to have to remove a hydrogen from the neighboring carbon, creating an alkene. Oops. All right, and according to my cheat sheet here, because primary carbons are so small and nice and accessible, our major product is that substitution product, and our minor product is that elimination product. All right, this alkoxide ion, specifically 2 carbons here, would be an ethoxide ion. This is a strong base, strong nucleophile. Again, good at both. So again, we're going to get a mixture of our elimination and our substitution. All right, if we do our substitution first here, make some room, shrink this down. All right, importantly, what am I going to have to make sure to do when I draw my substitution product? I have to do my stereochemical inversion. I got to flip about that electrophilic carbon, that dashed, dash to a wedge. All right, and attach that nucleophilic oxygen. If I'm going to do my E2 product, I'm going to remove a leaving group and a hydrogen from a neighboring carbon, but I got 2 different neighboring carbons here. So I actually have 2 different elimination products that I could draw. One, if I eliminate the hydrogen on the left, whoops. The other, if I eliminate the hydrogen on the right. Do I have any additional elimination products? Actually don't in this case. Why not? Oh, I guess I do down here. Yeah, you're right. I have one. I don't have an extra one up here because these 2 are identical, but I do have one more down here. The Z. So here's the E. Here's the Z. move this out of the way here. All right, but according to my cheat sheet here, what's my major and what's my minor? Elimination is the major and substitution is the minor, but we got to be good here. All right, which one of my elimination products is going to be the major elimination product? Because we have 3 of them here, A, B, and C. How do we determine? You go through our list. And what's the first thing on our list? Substitution, right? So A is what? Mono, di, tri, tetra. This one is a tri-substituted. And what are B and C? They are both di-substituted. This one's the E, this one's the Z. So we would definitely expect to have the most of A. We'd expect to have a little bit of B and even less of C, but we're just going to lump them together as our minor products here. So my major product is going to be my elimination product, and specifically that most substituted elimination product, most stable elimination product. All right, lastly, we're going to take this tertiary alkyl halide. We're going to react it with this neutral water molecule, which is a weak base and a weak nucleophile. That means it will undergo both SN1 and E1 reactions. All right, if I do my SN1, what's the functional group in my product? An alcohol, because remember that nucleophile, that neutral nucleophile is going to lose a hydrogen when it reacts in our substitution reaction. All right, and lastly, we're going to do our E1 product. There's actually 2 alkenes that we can draw here. These are both chemically identical, so it wouldn't matter which one I removed a hydrogen from. But this one back here is indeed chemically distinct, so that would give me a different product. All right, so our possible products here . Are either going to be one of these terminal alkenes, all right, or if instead we moved that double bond to the middle. All right, so we have our possible products here. Now we got to label them as major and minor. And again, this is probably a little bit of a lie and devil's in the details, but we're going to say that it pretty evenly favors substitution and elimination. So we're going to have 2 major products here. One substitution major product, our only substitution product. All right, but out of these elimination products, which one's going to be my major elimination product? The tri-substituted one on the bottom, we would call our di-substituted a minor product here. All right, so for these tertiaries, since we said it's pretty evenly split between substitution and elimination, we'll have both a major substitution and a major elimination product. But since you can have multiple elimination products, your major product is going to be the one that is the most stable, the most substituted. Cool. All right, so we got this when we're predicting our products here, our competition of substitution versus elimination, we got to figure out what our alkyl halide is, figure out what our reagent is, and then we can use our little cheat sheet chart here to determine whether it's substitution, elimination, or some combination of the 2 of them. Cool. All right, we're going to call it here.